Hello students, welcome to the second part of electromagnetism lesson. And here in this particular lesson we will discuss the rest of the parts of the electromagnetism concepts, that is the force experienced by the charged particle and what are the various cases involved in it, and after that we will go to the force experienced by the straight current carrying conductor, and then we will take our logic to the force experienced by the current carrying coil, and after that we will try to understand the working of the electric motor. So the force experienced by the charged particle kept in the magnetic field is given by F is equal to QVB sine theta, as you know that. And here in the figure 7, the magnetic field is into the board or into the plane of the paper, and then the charged particle with charge q is moving with a velocity v in the plane of the paper as shown. Now it will experience the force, and now see, according to the equation F is equal to qv sine theta, what are the various consequences of this particular equation. The first thing is that no force on the particle at rest or stationary particle. That means as V is equal to 0, the particle will not experience any force, which means that the magnetic field cannot apply the force on the stationary particles. So the magnetic field can apply the force only on the particles which are in motion only. The second point is that no force on the particle when it moves parallel to the field, as theta is 0 degrees. So when theta is 0 degrees, that means when the particle moves in the parallel direction to the magnetic field, in that case also, though it is moving, it will not experience any force. The third point is that even when the particle moves in the anti-parallel direction to the magnetic field, in that case also it will not experience any force, because theta is 180 degrees and sine 180 is 0. And coming to the fourth point, the force is maximum when the particle moves in the perpendicular direction to the magnetic field. So we know that when theta is 90 degrees, sine 90 is 1, that is the maximum possible value, and hence force experienced by the charged particle will be maximum when it moves in the perpendicular direction to the magnetic field. Please remember these points. Now, what about the direction of the force experienced by the charged particle? And this can be decided by the right hand rule. And see students, in our textbook there are two figures given, 8a and 8b. Both these things are actually right hand rule, and 8a is applicable when the angle between the velocity vector and magnetic induction vector is somewhere in between 0 and 90, and when they are perpendicular to each other we can use directly the right hand rule. And please remember this point, that it is very clearly given in the textbook itself that the right hand rule is for positive charges, because whatever the direction that you obtain with the right hand rule, it is applicable to the positive charges only. Then the question arises is that how to decide the direction for the negative charges. Yes, of course we can use the right hand rule for the negative charges also, but at the end you have to change the direction of the thumb. If it is east, you have to just say the westward direction the force is applied, and if it is north, it is a south direction, and if it is upwards, you have to say that the force experienced by the negative charge in the downward direction. And please remember that the direction will not change, only the magnitude will change. This is an important point. Now coming to the radius and time period of the calculation for this particle which is moving in the magnetic field, that you should remember that the fact is that the magnetic force always acts perpendicular to the velocity. That means it always acts as a centripetal force, and magnetic force cannot change the value of the magnitude of the velocity. It will only change the direction and make it into a circular motion. and then as this acts as a centripetal force, the equation for the centripetal force is mv square by r. So the force, magnetic force qvb is equated to mv square by r. So upon cancelling v and making r as a subject, we will get r is equal to mv by qb, and from that you can calculate the time period of the particle t is equal to 2 pi r by v, and upon substituting the value of v, we will get t is equal to 2 pi m by qb. Now see here in this animation that the charged particle is moving in a magnetic field, and here the magnetic field is coming out of the paper. So once when the magnetic field is coming out of the paper and the charge moves from right to left, then apply the right hand rule and understand yourself that the force experienced will be in the given direction. Now, regarding this particular concept, we should remember some of the key features. The first point is that as the magnitude of the velocity remains constant, kinetic energy remains constant. That is, magnetic force cannot change the kinetic energy. We cannot speed up the particle or we cannot slow down the particle with the magnetic force. Momentum changes as the direction of the velocity changes, and this is the main difference between electric force and magnetic force, because with the help of the electric force we can do so many things. Now see here, does the particle get acceleration due to the magnetic force? Of course, yes, because the particle is moving in a circular motion, and every particle in the circular motion is subjected to centripetal acceleration. Then if you really want to speed up the particle, what to do? Yes, we can increase the speed without changing the direction or with changing the direction with the help of electrical fields. Now coming to this, the next concept, that is how to calculate the force experienced by the charged conductor, that is a current carrying conductor kept in a magnetic field. So we will start the discussion with F is equal to QVB only, and after that see how we can derive this equation. So F is equal to QVB, and then time taken for the particle to move is nothing but simply the distance traveled by speed, so L by V, so that V is equal to L by T. Now if you substitute V is equal to L by T there, we'll get F is equal to Q into L by T into B, and now taking Q by T as I, you will get F is equal to ILB. And here the note is given very clearly that this equation holds well only when the direction of the electric current is perpendicular to the magnetic field. That means we have to apply this equation once when it is when the direction of the current carrying conductor is perpendicular to the magnetic field, that is actually given here. Now if for example there exists some angle, then it is F is equal to ILB sine theta. We have to use the sine theta because it is a cross product. You'll get a sine theta component. Now the most important activity in the electromagnetism lesson is activity 8. How do you demonstrate that a current carrying conductor experiences force when it is kept in a magnetic field? So here the arrangement goes like this. You have to take the two wooden sticks with small slits and then make the wire horizontal and apply the battery and allow the current to pass through it. And just you will see that the current will pass through the wire and then nothing happens. But once when you keep a horseshoe magnet as shown in figure, it will start experiencing the force. That means the current carrying conductor will start experiencing the force, and especially here the downward direction. And you can apply the right hand rule to determine the direction of the force. And please remember here the magnetic field direction is towards you. That's very important. And you align the other fingers in the proper order, then the thumb will be pointed towards the downward direction. Ensure yourself that it happens like this. And here, this is another important concept, that is what happens in that particular the force. And here, this is the exact diagram, it is there in your textbook, and now I have added the other components to make the point very clear. Here on the left side, the straight lines, that is arrow marks, are due to the horseshoe bar magnet, and the concentric circular magnetic field in the middle is due to the current carrying conductor, and you can apply simply the right hand thumb rule to decide the direction of the magnetic field, and the right side one is the resultant of all these two magnetic fields. And this almost looks like a thumbprint or fingerprint. So here the resultant of those two magnetic fields will be in the form of the 11C. So upper side, more amount of the magnetic field is created. That means magnetic induction is high at the upper side, and then it is lower at the bottom. And hence the conductor experiences a force from a high field intensity region to the lower field intensity region. That is, the conductor will be physically pushed downwards. Now, extending this logic to the electric motor, and here you have a motor, in the sense a coil, and it is kept in a magnetic field. And here we have to decide and satisfy ourselves that what are the various directions of the forces experienced by AB, BC, CD, and DA portions of the coil. Now see here, the AB and CD portions will always lie perpendicular to the magnetic field even though the coil is rotating. So hence the AB and CD parts of the coil experience a constant equal and opposite forces on them. And coming to the BC and AD portions, as the coil rotates due to these two forces, the angle between the current carrying conductor BC and AD with respect to the magnetic field will change, and as a result the force will change on BC and AD parts. It changes, and also it changes its direction and magnitude, and we will see it in an animation so that you can understand it in a better way. And then the same discussion goes here in this particular slide. It is there from your textbook, and you should remember that the net force on the coil is 0. The force due to AB and CDs are equal and opposite, and the forces due to BC and AD are also opposite and equal in amounts, so the net force on the coil is 0. And please remember, though the net force on the coil is 0, the coil can rotate. Please remember, when net force is 0, the coil cannot go from one place to another place, but it can rotate. And see students, in this particular animation you can understand whatever I have said. See here, once when you apply the battery and then the, say for example, the positive charges are moving, see about the forces that are acting on the sides which are perpendicular to the magnetic field. So they are equal and opposite. They are not changing their magnitudes. But what about the directions of the magnetic forces on the other two? See, that is changing in magnitude as well as in direction. Just look at it carefully. It is depicted very clearly, each and every aspect here in this particular animation. Now this is almost actually a motor, but you have to draw the motor diagram from your textbook. And here please remember that you should not forget to draw this plus and minus signs, because in the particular motor we apply the electric current, that means we take the source that is battery